Welcome. I'm Mike Snyder, and on behalf of Haag-Streit, I'd like to thank you all for joining us today for what I'm sure will be a very exciting and information-packed session. You all received some question cards. If you have any questions that you'd like to ask, please fill them out on these cards. Raise your hand, hold the card in the air, somebody will pick it up, and we'll circle them around. And we will get to as many questions throughout the session as we can. We're privileged today to have three luminaries, true giants in cataract surgery, Drs. Olsen, Hill, and Barrett, joining us from the three corners of the world. I am sure that you will gain many pearls, so get ready. Dr. Olsen is going to start off our program. Dr. Thomas Olsen earned both his medical degree and his doctorate in medicine, the Danish equivalent of a PhD, at Aarhus University in Denmark. He won the prize of Chambray International Award even as a young ophthalmologist. Since 1991, he has headed the Outpatient Cataract Service Center and serves as an associate research professor of ophthalmology at Aarhus University. He is currently very active both at the university and in private practice. Further, he has been president of the Scandinavian Society of Cataract and Refractive Surgeons and an active board member for ESCRS as well. He has also been vice president of the Danish Ophthalmological Society, board member of Acta Ophthalmologica, and the editorial boards of both Journal of Refractive Surgery and Journal of Cataract and Refractive Surgery. He has served as chairman of CatBase, the Danish National Quality Outcome Registry for Cataract Surgery, and is a co-founder and the current president of the IOL Power Club, a private scientific group of international experts within the field of biometry and IOL power calculations. Please join me in welcoming Dr. Olsen to the podium for his presentation, Olsen IOL Power Calculation Formula using the C constant and ray tracing. Dr. Olsen.
Thank you, Mike, for this nice presentation. I have to excuse you for my voice. We still have winter time in Denmark. I wish I'd come here earlier. Well, I would like to discuss important things about IOL power calculation. And I think we can improve much upon our standard methods. I will focus on two important issues that I found interesting. One is ray tracing and the other is the C constant. I hope to describe this for you. I have a few financial disclosures. I'm sure all of you are familiar with the way that the old thin lens formulas work, because you only have to read 2 pages in an optical textbook, and then you'll find that in order to find the power of the IOL inside the eye, you need the divergence at the posterior plane of the IOL, and you need divergence at the front part of the IOL, and by subtraction you get the power of the IOL in the eye. But there are important variables in this formula that I will discuss further on. First of all, we have to recognize the very first formula in the world was by Fyodorov, the Russian ophthalmologist who also invented the RK method. And one of his contributions is actually that he devised a method by which we could estimate the lens plane position in the eye. And he took the formula like, I hope you can see my pointing here. No, you cannot. Is there a strong pointer here somewhere, or is it? It's too far from me. Anyway, the ELP is the estimated lens plane position. And he calculated as depending on the radius of the curvature of the cornea and the diameter of the cornea, according to the formula you can see on the picture. This method was meant for iris clip lenses, and it's still in use in the SRKT and the holiday formulas today. Now, in practical terms, what are we doing when we do IOL power calculation? We just take a K reading, we take the actual length, and then, by surprise, we have an IOL power. But there's something going on behind the scenes. I want to stress this. And one of these things is actually the ELP that's built into the formula. Now, if you do it right, you will find that you might have an error on the average in your patients. And in that case, you need to correct your predictions by applying some constants. And there are a number of constants that you need to apply to the method in order to correct the offset method, the offset error you might have in your formula. But please pay attention to the fact that by doing so, you're only moving the whole pattern. You are not decreasing the spread. You are not making the spread less pronounced. So if we want accuracy, what should we have? First of all, we should have DLP. I'll come back to that in a moment. What about the axial length? Well, since 2000, we have been lucky enough to have the optical biometry by which you can measure the length of the eye with a very high accuracy. Compared to ultrasound, I think we have to say that the accuracy with the laser is about 10 times as much. So if you have an error of 0.2 millimeters with ultrasound, you're down to 0.02 with the laser. This error translates into a very tiny fraction of the diopter, actually 0.05 diopter on the average case. My question to you is, do you see this error on the average case in your patients? And you know the answer is no. So there must be other sources of error in the system. Before I go into the ELP, let's have a fresh look on the corneal power, because this is actually a very important part, and it's a dark horse in the game. What is the power of the cornea? Well, if we know the radii of curvature of the front and the back surface of the cornea, you can read page 3 in the optical textbook, and you can actually get a paraxial formula for the combined power of the front and the back surface of the cornea. I did that as a student in 1986, and I found out that if we assume that the ratio between the anterior and posterior curvature of the cornea was the same as in Gullstrand exact schematic eye, we would need an equivalent index of refraction of the cornea of 1.3315, which was quite lower than the ordinary index of refraction in all keratometers still in use, which is 1.3375. And I'll come back to that. It really means a lot. Now, if we just take a step backwards, and then we think about how do we describe optics of any refractive object. When we talk about ophthalmology, we often assume that the cornea is like a sphere or ellipsoid, or some transformations may be at work. What about exact ray tracing? Exact ray tracing is actually the most effective tool in optical engineering, and it does not need a model. So if we want to design a telescope or a camera, we take exact ray tracing. Many instruments are able to give you the exact elevation data of the corneal shape, both the anterior and the posterior surface of the cornea. And I will give you some results of experiments that we did with the Pentacam. The Pentacam is able to export the mapped elevation data. We imported these data into a commercial optical software for optical engineering called the CMAX system. It's kind of a standard in the industry. And by doing so, we could actually put up this model. This is an exact a real case, front surface, back surface of the cornea, and then we can begin tracing each ray through the system, only using Snell's law and nothing but Snell's law. And we can find out what is the effective focus of that ray tracing. So if we look at the point spread function at a certain image distance, we can analyze for when the focus is very focused, that must be the effective focal length of the cornea. Here's such an experiment. We have the image distance on the x-axis, and on the y-axis we have the intensity of the point spread function. One case, different pupil diameters. As you can see, if we increase or decrease the pupil, there's a slight shift in the effective focal length of the cornea. That is because the cornea has spherical aberration, right? But all in all, we also get the effective focal length of the cornea without any other assumptions than Snell's law and the mapped elevation data. And by doing so, when we compare our method to the other methods, like standard keratometry, there's a whole diopter difference. So if you take a keratometer with 1.3375, I'm sure you'll get a diopter reading of that device, which is 1 diopter too high. And then we have other metrics. We have the true net power and the total corneal refractive power of the Penacam. May be quite similar to the total corneal refractive power, which is also based on ray tracing. So the K reading on normal keratometers is actually 1 diopter too high than the true power of the cornea. That's my conclusion. Now, before you go home and use the ray-traced corneal power, beware that all the formulas out there, they have been calibrated against the wrong power, so you cannot just use the true corneal power and have nice results. Now, other sources of error, and now I'm coming back to the ELP, because if you take an estimate of what are the sources of error in the system, I have been talking about the K reading, I've been talking about the action length, now I'm talking about the ELP. It's actually almost half of the average source of error in your routine cases, depending on the formula. So we need to reconsider, can we improve the prediction of the lens plane? And here comes the new concept, which I have called the C constant. The C constant actually describes the position, the physical position of the implant inside the crystalline lens, the empty bag of the lens. Now, just step back and think about, we have left the world of iris clip lenses, right? We are all doing standardized surgery today. We do a Raxis, whether by hand or by laser, and we are very good at that. So what is left is actually the anatomy of the crystalline lens rather than the surgery. That's my point. And it really works. Why it works is because we now have very good instruments to measure the lens thickness and its position, and that's the clue to it. And the Lenstar is a very nice instrument, having good reproducible measurements of the lens thickness and also of the, on the posterior position of the IOL. I was hoping to show that, there it is. There you can see the IOL is sitting right there. You can measure it, and it's very accurate by laser to measure its position. If we do that on a large series of patients, you can get this kind of picture, where you see this is the IOL position in the eye. It's a distance from the corneal vertex. Now I have plotted it against the axial length. So you can see this is the anterior capsule and this is the posterior capsule. So what is this slide actually shows that the IOL is sitting in the back. No wonder I put it there. But the trick is it's a mathematical representation that you actually can use the pre-op data to predict the physical position of that lens. Now, so we have get rid of the K reading and the axial length, and now we are back to the anatomy of the anterior segment. That's the anterior chamfer depth and lens thickness, and then we have predicted the position of the implant. It's very important to realize that it's not dependent on the K reading nor the axial length, which is significant when we go to the post-LASIK cases. I won't talk about these cases today. Here you can see it works in practical. This is the predicted value, and this is the observed value as measured by the Lenstar. Now, to go with the physical position of the implant, we need a formula that can take into consideration the exact physical distances in the eye. Many years ago, I described a formula which is a paraxial ray tracing formula. We have recently modified it, so now we are using exact rating. And the advantage of this approach is that it can take the true corneal power, as I just described, and it can use the C constant, where you have the exact prediction of the position of the implant also. Here you can see the results, and these results have been published last year in JCRS. If we have the axial length on the x-axis and we have different formulas on the y-axis, I was happy to see that our formula was doing quite good over the axial length range, also in the short eyes, but maybe especially so in the long eyes, better than the SRKT, Haag-Streit, Holiday, and the Hofer. So in routine, these are routine cases. In routine cases, we were able to show that the mean absolute error was decreased by 14%. But if you count the number of high errors, more than one diopter, they were reduced by 85% as compared to the SRKT, for instance. Now, you may ask, what about short eyes and long eyes? Because these are the critical eyes. Anybody can do a calculation in a normal eye, right? And as you know, short eyes are more sensitive to measurement errors, and they're especially sensitive to the ELP error. Long eyes are not so sensitive to ELP, but they're depending on the action length and the K reading assumptions. Now, I have 100 eyes that I did not do myself. These eyes were from a clinic in Germany by Dr. Peter Hoffmann, and he has a large database on many different eyes. And I had the data, I did the calculations and sent the data back to him, so I had no touch on it. And we calculate for the Holiday 2, the Hofer Q, also the Oculus software, which is by Dr. Preussner from Germany. This is a ray tracing program like my own, and also my own system as a software called Faker Optics. Here you can see in the short eyes, the Holiday 2 was a bit disappointing, I would say. There's a large spread, as you can see. Next, the Hofer Q is doing better than the Holiday 2, and this has been published in other series as well. And the Oculus is actually doing a little better than the Hofer Q. But the Olsen formula is actually doing very good also in the short eyes. If we measure the mean absolute error, the difference appears even larger. Here you have the Holiday, Hofer, Oculus, and my own formula. So we are going down close to 0.4 diopters on the average, even in the small eyes. Now, what about the long eyes? For this series, we also included the Haag-Streit, and I was happy that Barret did all the calculations in these long eyes, so I'm happy to include his results as well. And again, we have Preussner and my own formula. Here you see the results. It's a bit crowded, but as you can see, on the left side, we have Oculus, which is doing very good in the long eyes. And also my own formula is doing very good with a very small, non-significant offset error from 0. And on the right side, you have a group of formulas, Holiday 1 and 2, and the Hofer, and also SRKT. What is about these formulas? They all predict with a hyperopic error in the long eyes. Why is that? Now, my question to you, if you have a formula where the corneal power is off by 1 diopter, you have an error of 1 diopter, and you have an eye where the IOL power is close to 0. What will the prediction error be in this formula as the IOL power approaches 0? If you give me the answer next time we meet, I'll be happy to collect those. So I would say the future looks bright. We can do much better than we do. Just remember one thing I'm trying to say. There's no magic in IOL power calculation. Thank you very much.
So we're going to throw out a couple of questions for Dr. Olsen. First, when you measured the postoperative position of the intraocular lens within the eye with the Lenstar, what percentage of patients were you able to capture the position of the implant?
This is a very good question. Well, it depends on the IOL type, I have to say. We were quite successful when we measured the Alcon type of IOL, and many of these lenses I just showed you were the classical SA60AT, the spheric IOL. Maybe because of the high refractive index of that IOL, it was quite easy in many cases to measure the exact position of that implant. When it comes to other types of IOL, we have varying results. If I'm to say a conclusion on that, I would say if the refractive index goes down, it's a little more difficult to get the exact position of that implant. But it's easy to check whether you do have an accurate measurement, because I want to see the anterior surface of the IOL and I want to see the posterior surface of the IOL, and you can actually take the thickness of that measurement and check whether this is the true lens sitting there. So there's a validation method when you are in doubt.
Okay, there's a question as to the C constant and whether it takes into account the entire volume of the crystalline lens in figuring out that constant. Do larger lenses tend to behave differently as far as the C constant relative to smaller lenses, where the effective lens position may end up relative to those front and back positions?
Well, I cannot answer for the question of the whole volume of the crystalline lens, because we did not do ultrasound measurements on the equator or any other scanning techniques. But I can answer the question whether there's a difference between long eyes and short eyes, and there's not. There's none, and that's really amazing for this concept, because you have exactly the same C constant, whether you have short eye with a thick lens or a long eye with a thin lens, you get exactly the same C constant. So I would like to say that the C constant appears to be rather unbiased by any of the other metrics of the eye that we know of.
Great, and the last question we'll go with the ray tracing, how dependent is the ray tracing among the different pupil sizes, and which simulation size did you use for when you were doing your ray tracing work?
Well, for the average case, if I don't know the pupil size, I would assume a 3 millimeter pupil. But you're quite right. If we have a spheric IOL, the pupil size matters. So you need to take into consideration whether it's a small or large pupil. Not so much if you have an aspheric IOL, because those lenses were designed not to be influenced by the pupil size. Saying that, we all assume that the cornea behaves as a normal cornea, and we have to be aware that in many cases the cornea may not be normal. But how do you know that? You don't know that before after surgery in many cases. But it's obvious if you're dealing with a post-LASIK case or other keratoconus or other abnormal corneas, you have to think just a bit to see if the pupil is in that area and that size that is within the method.
Thank you. Well, I think it's great that we're now able to do so much better with our spherical results, and I think we're going to move into toricity a bit. And I'm going to welcome Warren here. Warren Hill has been in private practice in Mesa, Arizona for the past 29 years. I know you guys can't believe that because he looks so darn young. He completed his ophthalmology training at University of Rochester and has since devoted the majority of his career to challenging anterior segment surgeries and the mathematics of intraocular lens power calculations. He's best known for helping all of the rest of us obtain accurate IOL power calculations. Dr. Hill has published extensively, serving as visiting professor for grand rounds at many institutions, has delivered 17 named lectureships, has presented more than 600 clinical papers at both national and international meetings in 34 different countries. He has performed live surgery at ophthalmology meetings on half of the world's continents. And in 2014, Dr. Hill gave the ASCRS Charles Kellman Innovators Lecture, and earlier this year received the University of Rochester's Lifetime Achievement Award. Dr. Hill is going to share some pearls of wisdom in his talk. Use the Lenstar LS900 to get your toric IOL right, how to best plan surgery. I'd like to welcome Dr. Hill to the podium. Thank you. Thank you, Michael.
Well, good afternoon. What a great pleasure it is to be here with two of the people that have definitely influenced my career, Thomas Olsen and Graham Barrett, people that I look to and think very highly of. So let's talk about the Toric IOL. How many of you here use the Toric IOL? Well, pretty much every hand goes up. It's really been one of the great advances in ophthalmology in more than the last decade, and it's an integral part of almost all of our practices. So especially those of you from outside the United States, you know that anybody who makes an IOL these days is also making a Toric IOL. So it's certainly something to which we really have to pay attention as our patients are requesting more and more the best unaided distance correction. So what is it that we need for the Toric IOL? Well, there's lots of ways to get information for this. We can look at the patient's spectacle refraction, and here we have about a diopter of against the rule astigmatism. We can look at small zone autokeratometry. Here's a little more than 3 diopters with the rule. Some simulated Ks, a little more than half a diopter. It looks like this is against the rule. Ray tracing Ks, and here's a little more than 3/4 of a diopter on the oblique meridian, and some more small zone autokeratometry, about 2 diopters with the rule. Now, would it be surprising to you to learn that all of these measurements were from the same eye of the same patient? And this is one of the problems we have with a Toric IOL. You know, what do we use and how do we deal with conflicting information in a way that allows us to get the best possible answer? So I'm kind of reminded of the story of the 6 blind men who were asked by the king to describe an elephant by touching different parts of his body, and each man asserted that the elephant was something different, like a rope, like a tree branch, like a hand fan, like a pipe, because they were all touching different parts. And the king really explains to them, you know what, you're all right. Each one of you is telling it differently because you touched a different part of the elephant. And the elephant really has all the features you describe. So there are now 6 new Cornea fellows at the university, and they're asked by the department chairman to calculate the orientation and power of a Toric IOL. And each asserted that the cornea is different using simulated Ks, auto Ks, Scheimpflug Ks, slit scanning Ks, manual Ks, ray tracing Ks, perhaps taking into account the patient's zodiac sign, mother's maiden name, favorite dessert, and shoe color. And the department chairman said, you know what, every one of you is correct. The cornea has all the features you described, but not all of these instruments are equally suited to the Toric IOL. And that's what we're going to talk about today. We're going to talk about how to sort of touch the cornea with our measurement techniques and come up with the right answer. So how do we know which is correct? Well, those of you who know me like to, or know that I like to steal things from other specialties, and there are lots of other organizations, professionals that deal with conflicting information and have to come up with the right answer. And one of those people, one of those groups rather, are airline pilots. You know, they make a mistake and someone's going to have a really bad day and you might end up on CNN. So how do pilots deal with conflicting information? Let's say they're flying from here to Minneapolis and one of their 6 important instruments goes bad. How do they know? Well, we have in aviation what we call the triangle of agreement. So let's say we're flying from here to New York City and we want to know what our course is. We use something called a heading indicator. That's like a compass, except it's a little bit more complicated. And here, when the heading indicator says it's not making a turn, you know that it's working right. But let's say, what if that instrument froze and just stood there and didn't make any changes? Well, we have backup instrumentation. So the heading indicator would be primary for what we're looking to do, and 2 other instruments called an attitude indicator and a turn and bank indicator are secondary. They all give us the similar information. One is primary and one is secondary, and if they all agree and they all work by different methods, we know that we're probably on a solid footing. A primary instrument is one that always gives us the correct information when it's presented a certain way, and we can use that for the Toric IOL. A supporting instrument is one that helps us to understand that that's correct. So here we have our 3 instruments. Our heading indicator says we're going this way. Turn and bank indicator tells us we're not making a turn. Attitude indicator tells us we're not making a turn either. So if our attitude indicator suddenly says we're in a descending right turn and all the other things are correct, we know that that instrument is probably the one to not be correct. So again, we're not just using multiple instruments, we're using multiple instruments in certain ways with primary and secondary roles. So let's take this way of thinking and move it over to what we do for the Toric IOL. Now, the Toric calculator, there's a lot of things we put into it, but the 2 main things the Toric calculators are looking for is what is the orientation of the steep and the flat meridians, and we need to know the power difference between meridians. Said a different way, that's our corneal astigmatism. So here's our primary instrument. This is our heading indicator for the toric IOL. It's just the humble axial map for the cornea. And here we're going to look at the Zeiss Atlas Topographer, which is one of the standard instruments for this, kind of an industry standard. And if you look at the central 3.5 millimeters, draw a line through the corneal vertex and the center of each of the two astigmatic lobes, where it intersects the axis scale and the periphery, can only be the steep meridian. Again, a primary instrument is one that always gives us the correct information when presented a certain way. Now, if we look at our keratometry, we look and see, is the keratometer measuring in the correct place? We look and see if the keratometer says that our steep meridian is the same as what we already know to be correct. So keratometry is primary for the power difference between if it's measuring in the right location, and secondary to confirm the steep meridian. So these are just the two things you need. You need a topographer and you need a good source of keratometry. So let's look at another axial map. This is the T-cone from the Lenstar. Believe it or not, the Lenstar actually has a device that sits on the front that gives us an axial topographic map. Looks very much like the Zeiss Atlas 9000 topographer. So there's our 3 millimeter zone for this. There's our steep meridian. There's our flat meridian. And just to repeat, this is primary for the steep meridian, secondary for the power difference. There's our Ks. We make sure that the two line up properly, and now we know what the orientation is of the steep meridian and what the power difference is between. So this is what the T-cone looks like. It goes on right in the front of the Lenstar. We like to joke that this turns the Lenstar into a Swiss Army knife. Basically, it doesn't have a toothpick and a spoon, but it has just about everything else. And it looks just like the Zeiss Atlas Topographer. It has the same sort of placido rings, and the measurement area is about 6 millimeters instead of 9 millimeters. And it was validated against the Atlas 9000 Topographer and came out almost exactly the same, both for normal eyes, spherical eyes, and astigmatic eyes, and also valid against the Lenstar Ks, which are, in my opinion, are the best Ks in the business. So this can be used with confidence in place of just the regular Ks on the Lenstar, and it also gives us an axial topographic map. This is what it looks like. You can see it's not very intrusive, sits right in front of the patient's eye. With a single button push, you get the topographic map, your Ks, and also all the axial measurements. Now you don't only get that, but you get several other types of topographic maps. And if we just look at the axial map right here, you click on that, and there's what it looks like expanded. And then here's what we can use for determining the steep and flat meridians, and then the keratometry values for the power difference between. So this is pretty much all in one, everything you need for that part of the toric IOL. Now also on the Lenstar is a wonderful little line that you can move to the left and right, and you can superimpose the topographic map on the image of the eye, line everything up, and read the steep meridian with this all-in-one device. So let's talk about different types of keratometers and why this is slightly different. Here's the original IOL master strategy for keratometry. We have 3 measurements above, 3 measurements below the horizontal, and it's a 2.5 millimeter zone. This instrument was originally designed for the spherical power of the lens. It was not designed for torics, and that's why we sometimes get surprises. If you look at the center measurement here, this device measures at 60, 120, and 180. So at 90 and between the 120 and 180 measurement, the instrument has to do some extrapolation. So that's why it has some blind spots and why we can sometimes get a surprise. This is how keratometry works. Basically, we look at almost like a double sine wave. We have where it has the greatest power, we look at where that meridian occurs, and basically that's our steep and our flat meridians. But you can see a fair amount of iteration has to take place between points in order to come up with something. And those of us who've used the IOL Master know that between 60 and 120 is 90, and that instrument always seems to have the most trouble at 90 because that's where it's doing most of its iteration. This is the Lenstar. It has 2 zones, 2.3 and 1.65 millimeters. There's the outer zone. Here's the inner zone right here, inner ring rather. And if we look at the first measurement, we can see that the distance between measurement points is not very great. So there's very little iteration that has to take place. So this is what's referred to as high density autokeratometry. And if we look at this instrument compared to the one before, you can see that there's one ring, here's our second ring, Here's our steep and our flat meridians. You can see very little iteration takes place. So this higher density form of keratometry is better suited to detecting both the steep and the flat meridian and also the power difference. Anybody read Russian? There you go. There's one person. Okay. Trust but verify. Okay. So just a couple other quick things about it, and I know Dr. Barrett's going to talk about his toric method. The iSuite Toric IOL Planner, which is a kind of a separate piece of software that you can add on, gives you the Barret formula, the Barret Calculator, which adds the posterior cornea, which allows that calculator to use a third vector for the calculation of the orientation of the steep meridian. And this is what I use in my own practice, and it works very, very nicely. It's becoming a standard. For the Barret Toric Calculator, we use a surgically induced astigmatism value that's a centroid value, which is 0.12, which is what we're using. Also, you can go online. There's a tool for calculating surgically induced astigmatism that will give a median, a mean, and also a centroid value, and that's at siacalculator.com. So you can actually come up with this value yourself. I've stopped marking the cornea. Instead, I use the image off of the Lenstar, and if you click in this one little area in the upper right-hand corner that's highlighted, here I've marked 4 different landmarks that won't go away with dilation, and I take this, hang it upside down on the microscope, and now I know exactly where these 4 points are, and it does a lot better job for us as far as determining references and where to put the toric IOL. I also like to have Dr. Olsen's formula and Dr. Barrett's formula both displayed for my favorite intraocular lens, and I look at them at the same time when I'm making decisions regarding intraocular lens power. And just a couple quick comments about the instrument. All of the measurements are done by optical biometry, so central corneal thickness, aqueous depth, anterior chamber depth, lens thickness, and then the axial length are all by optical biometry. The current version of the Lenstar just uses a slit image estimation for the anterior chamber depth. And not only does it give it a lens thickness, but you can actually see all the component parts of the lens. Now, there's the anterior capsule, the cortex nucleus interface, different parts of the nucleus, and the posterior capsule. How thick is the posterior capsule? It's about 5 to 7 microns. That's the thickness of a red blood cell, and here we have a signal with the Lenstar. So the accuracy here is really, quite remarkable compared to what the IOLmaster does, which is just a global measurement from the corneal vertex to the pigment epithelium. And then one last thing I'll leave you with is validation criteria. Remember, a measurement's only as good as our ability to know what it means, and if something comes up that may not be quite right, we need to be able to pick it up. And this is downloadable from the Haag-Streit website. This is the validation criteria, say, for keratometry. We look at the standard deviation and make sure that it's within these ranges. And each part of the measurement process from Haag-Streit has validation criteria that we and our staff can use to make sure that things are right. And if something isn't quite right, then we go back and we remeasure. As the carpenters say, we measure twice and we cut once. So in summary, this is high-resolution measurements of the central corneal thickness, anterior chamber depth, lens thickness, and axial length. We now have the T-cone, which is a topographic device for a biometer. That's a first. And the topographic map validates the orientation of the steep meridian, also tells us do we have regular symmetrical astigmatism. The steep meridian validates the power difference between the 2 principal meridians of the cornea. This is a highly accurate method that allows us to do the toric IOL with a lot of predictability. It also has the most sophisticated formulas, Dr. Olsen's formula and Dr. Barrett's formula, which we rely on now exclusively in our practice. And it has an integrated Barret Toric Calculator that Dr. Barrett will talk about in a few minutes, and multiple landmark site identification for toric IOL placement. Really, this truly is a Swiss Army knife. It's just an amazing instrument for biometry. Thank you.
Warren, thank you so much. Every time you talk, I'm furiously writing down notes and trying to keep them all mentally packed into my head because there's always so many great pearls of wisdom to share. A couple of questions. First, what if somebody out there doesn't have a topographer? All they've got at their office is one unit, a keratometer. Is it reasonable to perform toric corrections with toric implant lenses or other astigmatic corrections in that setting?
Yeah, that's a great question. Well, actually, you need a topographer. It's just something you have to have. And it gives you three pieces of information. One is the astigmatism regular. Is it symmetrical? And what's the orientation of the steep meridian? So you really do have to have a topographer, Mike.
Can you explain to us a little bit more about the centroid? What is a centroid? What does that mean?
Yeah, well, centroid is just one of the ways we look at our outcomes. You can take a mean, which is an average, a median, which is, in essence, a median just gets rid of some of the outliers. And a centroid is the kind of the mass center of your data plotted in 2 dimensions. If you have an error, what happens is the centroid shifts to the right, to the left, to the up or down, and you get some insight as to perhaps what the origin of this error might be. When your collection of data in 2 dimensions, and like a double angle plot where it's axis and then power, if all of your data clusters in the middle, then you know pretty much you're not dealing with some bias in the calculation. The Barret calculator works best with a centroid value, and that surgically induced astigmatism calculator will provide a centroid for your database.
And with the T-cone attachment, we can obtain both the keratometry and the simulated keratometry from the topographic measurements. Do you find the T-cone as accurate as what you've described as the gold standard in the industry for the keratometry taken without the T-cone on the Lenstar?
Yeah, that was part of that study that I presented, and basically it's better than a quarter diopter accuracy of the keratometry of the Lenstar, so it's really spectacular.
That's absolutely just awesome stuff. Well, as we've now got a little bit better idea about how to jump into our toric work, we're going to hear Dr. Graham Barrett talk to us about the toric calculations and how to approach that. Now, Dr. Barrett is absolutely a gifted cataract and keratorefractive surgeon, and he's joining us all the way from Perth, Australia. So I think he has the biggest time change of anybody in the room. I think it's exactly 12 hours, is it? Professor Barrett is a gem in Australia, and he's been recognized worldwide for his numerous contributions to peer-reviewed papers, many textbook chapters. He's produced several award-winning videos on cataract and refractive surgery, and he's also the recipient of the Harold Ridley Medal, as well as the equally prestigious Binkhorst Medal. His special areas of interest include lens prediction formulae, new techniques in cataract surgery and intraocular lens implantation, intraocular implant lens design, as well as refractive surgical techniques. Professor Barrett has served on the boards and editorial boards of the Journal of Cataract and Refractive Surgery, the European Journal of Implant and Refractive Surgery. Graham has been past international representative for the Asia-Pacific region of the International Society of Refractive Keratoplasty. He is currently a board member of the International Society of Refractive Surgeons and the president of the International Intraocular Implant Club, president of the Asia-Pacific Association for Cataract and Refractive Surgeons, and is also the current and founding president of the Australasian Society of Cataract and Refractive Surgeons. Please join me in welcoming Dr. Graham Barrett to the podium for his talk on the toric enigma, cracking the code.
Thank you very much for the introduction and for the opportunity to speak at this interesting symposium. So as you've heard, we do have methods today which enable us to predict eyes accurately regardless of axial length, post-refractive patients. But toric lenses are more challenging because we need to choose not only the spherical power of the lens, we have to choose the cylinder power of the lens, as well as the axis of orientation. And it's an enigma that despite very careful methods of measurement today with accurate biometry, making sure that we align the lens accurately on the correct axis, sometimes still we have a surprise, and the predicted residual astigmatism is not what we expect. The predicted residual astigmatism is simply the sum of the cylinder power of the toric lens at the corneal plane plus the predicted corneal astigmatism from the measured K and the formulae. And the error in predicted residual astigmatism is the difference between the actual refraction and the predicted residual astigmatism. And you can express this as a percentage of cases predicted within a half diopter, or you can express it in terms of the centroid value. And as Warren's explained, this is a true vector expressing both the cylinder magnitude and axis. The best way to look at results graphically is to do what's called a double plot graph. So you see it goes from 0 to 180 rather than to 0 to 360. And if you plot the xy coordinates of each vector, you can get a graphical display of the results of your analysis. Our understanding of the cornea really began with the development of the first keratometer by Javal in the 19th century. And he was practicing in Paris in the 1800s, and he made an observation. And the observation was simply that when he measured the anterior surface with his newly developed keratometer, he couldn't fully explain ocular astigmatism. There was about a half diopter of against the rule astigmatism, and he termed this Javal's rule. And he thought, indeed, even all those years ago, that the posterior cornea was responsible for this a half diopter of unexplained against the rule astigmatism. And we kind of conveniently forgot about the importance of this observation until Doug Koch, in his Innovators lecture in 2012, reminded us that Javal's rule was still important for toric IOL prediction. He further showed that there is a relationship of with the rule astigmatism and the posterior corneal astigmatism, but no relationship of against the rule astigmatism and the astigmatism of the anterior surface. But the bottom line is, if you ignore posterior corneal astigmatism, you will overcorrect patients with the rule astigmatism by about a half diopter, and you will undercorrect your patients with against the rule astigmatism by about 0.3 diopters. Now, one of the ways you can compensate for this observation is to use the nomogram developed by Doug Koch and Li Wang, the Baylor nomogram. Or you could actually use Scheinflug imagery, either Galileo or Pentacam, and measure the posterior cornea. The alternative is my approach. So what I have proposed is a theoretical model to explain the observed behavior of the posterior cornea. And it's quite straightforward. And it is simply an observation that the corneal architecture is quite unique. It's elliptical. And the horizontal diameter is always greater than the vertical. Therefore, the vertical radius of the cornea will always be steeper than the horizontal. And it's this elliptical cornea which explains why you have a half diopter of against the rule astigmatism contributed by the posterior cornea. Now, my own universal formula predicts the corneal diameter at the ciliary plane, and it was therefore not too difficult to extend that, to use the formula to provide both the vertical radius and the horizontal radius, and therefore calculate what the posterior cornea is without actually measuring it based on the axial length, K, optical ACD, etc. One of the confounding factors when you analyze astigmatism is the fact that we create an incision when we do toric lenses, and this creates surgical-induced astigmatism. The other error which confounds analysis is the fact that the lens may not be on the axis that you intend it to be, but you can compensate for those factors by using the post-op Ks rather than the pre-op Ks in your analysis, and measuring where the lens is actually sitting. And we did this in 68 patients from a data set derived in Ain Tal in Israel. Now, all calculators basically use the same vector maths, which essentially you convert the cylinder into x, y, or sine and cosine derivatives. That's all the same for whatever calculator you use, but there are significant differences. So the Alcon calculator, for example, uses a constant ratio in converting where the toric cylinder is to the corneal plane, regardless of the axial length or regardless of the toric cylinder power itself. If you look at the percentage of patients within a half diopter of intended residual error, With the Alcon calculator, only 33.3% will be within a half diopter. And you can see that the centroid value is 0.52 diopters of against the rule astigmatism. The Holiday calculator, which is the basis for the AMO calculator, does calculate the ELP and use that value to transfer the toric cylinder to the corneal plane, which is correct. But you can see that the improvement is quite modest, only up to 35% now, within a half diopter of intended residual astigmatism. And the centroid is once again very similar at 0.55 diopters. Now the same data set with my own calculator, which does calculate an accurate ELP to take this toric cylinder to the corneal plane, but also, as I've explained, has an integrated solution for the posterior cornea, now has 72% of patients within a half diopter of intended astigmatism, and the centroid in this situation is now close to 0. So these are not small differences in outcome, quite substantial. We did a second study with my fellow, Adi Abulafia, and here we used my own patients, 54 eyes of my own patients who had toric lens implanted, and in addition to the post-op Ks, we measured the pentacam, pre and post-op as well, to look at the influence of both the baleonomogram as well as direct measurements of the pentacam in the calculations. And if you want to try and solve this puzzle, this enigma of toric lenses, what we did was compared what would have happened if we used pre-op versus post-op Ks, what happens when you use the intended versus the actual axis of astigmatism, and what happens when you use different calculators to try and work out the relative contribution of each of these factors to the error in predicted residual astigmatism. So there's really three scenarios. The first scenario, you use an assumed SIA and assumed axis of alignment. Scenario 2, you know the SIA, you use the assumed or intended axis of alignment. And scenario 3 is where you know what the SIA is by using the post-op Ks, and you know the axis alignment by having measured where the lens is sitting. So scenario 1 is where most of us operate today. We use pre-op Ks with an assumed value for the SIA, and we assume the lens is sitting where we intend it to be. So here you can see with the Alcon calculator, about 10% of your patients will be within a half diopter of what you intend. With my own calculator, 50% of patients in this circumstance are within a half diopter. This is using a median value for SIA. And as Warren's explained, that's not the most appropriate value. And if you use a centroid value for the surgical induced astigmatism, taking not just the magnitude but the axis as well in the calculation, you can see both calculators improve significantly. If you then use the post-op Ks rather than the pre-op Ks, so if you eliminated SIA as a confounding factor, there's a substantial improvement. 70% of patients now are within a half diopter versus maybe 30% for the Alcon calculator. And finally, if you use the actual axis of alignment where the lens is sitting, not where you think it should be sitting, surprisingly, the improvement is only quite modest, which you would have expected that to be a greater source of error, but it's not. It's best to display this graphically on a double angle plot, and as you can see, there is that against the rule residual error with the Alcon calculator versus my own calculator where the centroid value is close to 0. And if you look at the Holiday calculator, for instance, on its own, or if you modify the K by using the baleonomogram, or by modifying the K using the pentacam, you see there is an improvement, up to 50% using the baleonomogram. But this is still not within range of my own calculator where patients will be within a half diopter in about 70.4% of cases. So in resolving the toric enigma, the first thing to note, of course, is that the centroid value of SIA is important, and that your surgical SIA is something which does confound your results. The second thing to note is that errors in axis alignment is important, but not as great a factor as you may think. And the most important factor in improving your results is to use an improved method of calculation. There's many different ways to improve your axis of alignment with toric IOLs. There's instruments containing little spirit levels, gravity-based instruments, imaging apps, and even instruments incorporating a horizontal line indicator. Even more sophisticated, you can consider using intraoperative aberrometry to try and find out the toric axis and where to align it, or you could use image-guided systems such as the Varion to help you mark the axis correctly. Personally, I find the handheld devices somewhat fiddly, and the image-guided and wavefront aberrometry are quite a complex and somewhat expensive solution. So my own practice is to use something called the Tory Cam Approach. And this is an app I developed which is really quite simple but an accurate method of toric marking. And you simply need the app and a felt tip marking pen. So I dry the limbus carefully with a spear and then mark where I think 180 degrees is, but I'm not too fussed, because then I take the app and I align the red reference axis with my inked marks, and that tells me exactly the reference axis angle. It's supposed to be 180 degrees, but if it's not, it will tell me exactly what it is. You press the button, you take a few images, and you can then press the Tory Cam logo, and it will display the last 5 images. And you can select the one which you think is the best match, and that will display the patient's name, the date, and the true reference axis. Once you have the true reference axis, you can then use that to offset your toric axis marker, mark the cornea, and then in this case I use the Varion, and you can see that the Varion axis exactly marks the axis that I marked from my Tory Cam app. A nice confirmation. And after the surgery, I always operate on a consistent axis. I think that's important in trying to predict your SIA. The idea of operating on a steep axis is just going to confound things terribly. And then when you implant your lens, you have marks that you can align your toric lens with great confidence. Now, I've done several cases with the app and the Varion, and they always give me the identical result. So you have a choice, image-guided versus the Tory Cam app. I've also developed a new marker, and this marker has a dual axis. So you can set the reference axis with the outer rim separately from the toric axis, which you derive from the calculator. And then it's quite simple to simply take this information from the calculator, from the Tory Cam app, put it in the marker, and press on the cornea, and you have some very nicely defined marks from which to align your toric lens. I don't have a financial interest in the app or the marker, but the marker is available from Haag-Streit if you're interested. And I've looked at the axis error from where I think my 180 reference axis is to what the Tory Cam app indicates it actually is. You can see that my average error is quite small, 3.2 degrees. That means I'm pretty good at actually eyeballing where 180 degrees is. The error is quite small. But some cases, as you can see in this frequency distribution, do have up to 8 degrees of axis alignment error as far as the reference axis, and they would certainly benefit from application of the Tory Cam app. And the final element in toric planning is what happens if you get a result which is not what you expect, an unexpected outcome. What are the strategies that you can use to try and correct that? Well, this is the new formula which has just gone online called the RX formula, and you simply enter your post-op data, and this will tell you on the same formula what your lens could be exchanged for, what your piggyback lens should be, both from spherical and toric power, and where you should rotate your existing lens to try and minimize your astigmatism. So with all these strategies, I think you can solve that enigma. You can operate on axis, not on axis, but on a consistent axis, you should use an SIA, which is the centroid value, 0.12 rather than 0.3. Try and minimize any axis misalignment by using different strategies, and I've shared the Tory Cam app as one way to approach this. And most important of all, use a method of calculation which is accurate, which does incorporate both a predicted ELP but a solution for the posterior cornea. And thank you for your attention.
Graham, thank you so much for sharing that brilliant information with us. You know, I'm a data guy, and the data that you showed is really amazing, and clearly your formula hits much closer to the center of the target. Do you have any thoughts to share with us? Why is that better than actually measuring the posterior cornea? Do you think it's that we just don't have good enough equipment to measure the formula? What is your explanation for why this has come out so good?
So, Mark, it's a good question because it's not what you would expect. You would think that direct measurements would provide you a more accurate outcome, but they don't, not even close. So it tells you one of two things. Either that the technology that's being used is not measuring the surface accurately, or maybe there is something inherently about that surface which makes it difficult to measure. And there are some people who propose that perhaps the posterior cornea is not orthogonal, for instance. So you may be trying to get consistent axes on something which it may be very difficult to do so.
Well, I think we've used up our time. I'd like to thank you all for joining us today, and we hope that you'll take home lots of useful tidbits and pearls to your practices. I'd also like to briefly mention that we just recently got FDA approval, and the Haag-Streit microscope for the operative environment now has intraoperative OCT, and it's a pretty cool technology. So if any of you are interested, I'd encourage you to stop by the Haag-Streit booth to check that out. And hope you enjoyed the presentation today and enjoyed the rest of the conference. Thanks very much, and I'd like to thank our panelists for just really fantastic presentations.